Yeah. Hello everyone. Are you able to hear me?
Yes, you're audible.
Okay. So, so today we'll go through the last week of the content. So did you submit like everybody has submitted that for the like graded for the 11th week? Did you submit?
Uh, no, sir. I think the due date is still pending. Right?
Okay. Yeah, the due date is 24, but there's not much like difficult problems in the 11th week, right? All the
Okay,
concepts.
yeah, I have come. You meant like, have you tried it or completed it or something?
Only the
Yeah,
transformation is the new concept. Other than that, everything I guess has been covered in stats 1 or 2, right?
yes.
Excuse
So
me, sir.
yeah,
Sir, I have doubt in one activity question.
okay,
So activity 11.4.
okay, 11.4,
So question 1.
11.4 question 1. Which of the following is correct? Yeah. In which option you have the problem? All first
So in
one,
second option.
second one. Okay. So if A is less than B and C is less than D, then F comma B minus C. Okay. Okay. So if you try to just okay, so you can take some value A, B, C, D. Okay, so where A can be less than B and C can be less than D. And then if you'll try to do this, you'll get a rectangle, I guess. And
So can you solve me in front of
okay,
solve this in front of me?
yeah. So 1 second, I'll just share the screen. So this is 10.4, right? 10.4, week 10. Okay, 11.4. This is 11.4, right? 11.
Yes, sir. Yes, sir.
Mm, mm. पानी दियो पानी. This problem, right?
Yes, sir.
Yeah, audible. Okay. So which of the following properties of the CDF? Okay. So first one is correct. Okay. Third one, only second one, right? So what we can do is, so we'll just take some values A, B, C, D. Okay, some random values, and then we'll try to do this. And then I'll just connect my vacuum. One second, I'll just connect my charger also. Where is that? So I'll just take some random value now. And what I need to prove is this one. So A should be less than B, and then C is less than D. What else is there? Okay, I need to show that f of the CDF of B comma D. So just if you are able to plot this, like for example, I took some values A and B, okay, and uh, and then took CD, F comma BD, D. So can you tell me what is written there? F comma BD, then uh,
minus
Yes,
f of
sir.
b comma c,
hmm,
uh, minus f of
Minus f of
a
a
comma
comma
d,
d
minus
plus f of a comma c.
f of a comma d
hmm,
plus f of a comma c.
A comma C.
Yeah, it is greater than or equal to 0.
Okay. Anything else has been given here? Nothing else. Okay. Okay. So you can take such that, let's, for example, I'm taking this as a x1, okay, and this as a y1, this as x2, and this as y2. Okay. So I can represent it here. So I'm just taking some random value. Okay. This is x, and this, sorry, hmm, some random values I'm taking. This is y, and this is x. Okay. And x1 is here because x1 is less than x2, and this is x1 and this is x2. Here we are getting y1, and here it is y2, right? Or you can say whatever you want to represent, a, b, and c, d, right? If I'm having a plot, yeah, is there like, okay, okay, so f of b comma a, b comma d, what is this? B comma d is here. If I'm having some plot, some random plot. Okay. So is there anything given? Okay, CDF. Okay, fine. So if I'm plotting, this, if I'm having plotting this and then this one, generally presenting what? F comma BD is what? Okay, so F comma BD is simply less than. So what does this mean for the probability such that the X is less than B and Y is less than D, right? So this is the area, right?
Yes,
This, right?
the
This
rectangle.
total area. This one is this one. And this what this is asking me, it should be greater than equals to 0. So this is what, if you will see that F comma BD is this area, total area, and then minus BC. Then BC is what? BC is this one, right? So if you'll just try to see this, I think so. This will represent which area? So the total, if you'll see this, F comma B is this one, is total till here, the area. And then B comma C is what? B comma C, B comma C. Okay, so we need to reduce this. So we are left with this area. And then minus AD. AD is what? AD, A, where is this? A is here and D. So if we will reduce it here, okay. So We'll be left with this area, and we are reducing this area twice. Okay, so we are just adding it so that we'll be left with this area only, and that is greater than equals to 0. This is what I think to ask. See, I'll explain you again. So I took a lot of time. It's fine. So I just a comma b. So we can take some values on the x-axis, that is a comma a b, such that x1 is less than x2. That you can plot it here. We plotted it here, and then take some values y1 or y2 and plot it here. If you have plotted it, if you will see whatever is written here, it should be greater than equals to 0. That has been asked in the second statement. And if you will see this, f of bd is what? Probability such that x is less than equals to b and y is less than equals to d. That means the area under this, right? I think your voice, I can't hear. Is this a problem from my side or her side?
No, sir. No, it is breaking up.
So there is problem here because it's raining outside.
What training?
Internet connection.
It is, I think she said it is raining
So
outside.
it is raining.
Okay, raining. Yeah, it's raining. It's at my place also.
That is the internet connection.
Okay. So did you understand this, or should I repeat this?
Yes, yes. Sir, one doubt here.
Okay.
So if f of b comma d, I understood this whole square thing or rectangle thing, and then minus f of b comma c is the lower part. We reduce the lower part. Minus we reduce the like left side part,
Yeah.
and
So
then we left with the square. Then why are we adding this f of a comma c?
see, f of bd is total area, right? And then we are reducing b comma c. That means we are cutting down this one, this much, right? B comma c is what? This is a, this is b,
Yeah.
this is c, this is d. So we are reducing this one. So we are left with this
Okay.
area, right?
Yeah.
And
Yeah.
now what we are doing, we are reducing a comma d. So what we have already reduced this area, right? So we are left with only this much. Like, see, we are left with just this much, this area.
Yes.
Okay. And again we are reducing, we don't have this much area, because see, this area we already reduced, and now this is asking to
Yeah,
reduce a comma d. So a comma d is here. So this again, this is asking me to reduce this area. This is asking me to reduce this area. Okay, so I was having this area already, so I reduced it, but this area I was not having, right? So this area I have reduced, but I need to add it, because this I was not having, right? Because this area we have reduced it when we were reducing f of b comma c. So we are you able to get the point, or should I do?
After reducing, yes,
It
sir.
is.
So after reducing this f of a comma d, we are left with that rectangle a b c. Then by adding this thing f of a comma b.
No. See, so when we have reduced, we first we took this total area, then we reduced this area. So now we are left with this area only. Now we are left with what? This is A, this is B, this is C, and this is D. So we are left with this area only. So this is the area till here.
Yes.
That was okay. And now we are reducing a comma d. So when we are reducing, because we were, so let's for example this is having some alpha value, right? And this is having some beta. Okay. So what we are reducing, alpha plus beta we are reducing, but we have only alpha, right? So will be what if we are reducing, so beta minus alpha plus beta will be having minus alpha.
Yeah.
Okay, so this alpha we need to add it again. So that's why we have added this f of a comma c, just to neutralize this one.
Okay.
So we have added
So
this.
finally we'll have this figure A B C D, this rectangle which you have drawn now, and and plus this alpha part.
This alpha, not finally we will having only rectangular part.
Okay.
Because see, we were having this much area, and then we reduced this area, but this area was not like we were not having this area because we already have reduced. So we reduce this area. Okay, so we are reducing alpha also. So to neutralize it, we'll add the alpha. So we'll be left with this rectangular area, and the area of a rectangle should be greater than equals to 0, right?
Yes, sir. Thank you, sir. So, in lecture 11.6 also, I have problem in transform random variables. If you can just tell us the concepts once again.
Okay, I'll
It's a
just,
keyboard.
yeah. 11.6, right? Okay, so I'll just go through the slide. So the transformation, yesterday we have discussed it, but I'll go through that. So see, the transformation is not that, see, what we are doing, there are generally three steps that we do to transform any, if we have been given to transform the random variable, multiple random variables, okay? So I'll just go through the basic steps, what we generally do in transformation. So see, in stats 2, you would have read in stats 2 what you read. In stats 2, you would have read how to transform a simple random variable. If you have been given the distribution of x, and if you have been asked to calculate the distribution of some equation, like for example x square, and this x square, for example, and x generally is varying from 0 to 1, then only you'll be
Yeah,
able to
it's
do with the
similar
form.
to function of random variable.
Yeah, so at that time what you used to do, so if you have been asked to calculate the distribution of this, so you used to do like whatever you have been given the x distribution, and then you were doing some basic formula you were using. Okay, so the same thing we are doing it here, but the here we were dealing with multiple random variables. Okay, so in multiple random variables we'll be having three steps mostly. The first step, so the steps to for the transformation, right? So I'll just give you one example. Okay. So like for example, for x, so you have been given the distribution of fxy, right? So the steps later. Okay. So if you have been given the distribution of fxy, okay, some distribution you have been given. So joint distribution you have been given of xy. And you have been given the transformation also. Like for example, u is given in such way using the form of some transform value like x plus y by 2, and v is also given such that x minus y by 2, or anything it has been given. So you have been given the joint distribution of xy, and you have been given the transformed random variable also. And now you have been asked to calculate the distribution of fuv. Okay, so in such cases, what you will do is just first see whether you are able to write this xy in the form of uv or not. So here, for this example, we'll be able to write the xy in the form of uv. Okay, so this means it is invertible, simple invertible. Okay, so the simple formula for this is, if you have to write the joint distribution of uv, so generally this can be represented like this: xy multiplied with the Jacobian. Okay, and Jacobian, how generally you calculate the Jacobian? So to calculate the Jacobian, you need to write x and y in the form of u and v, right? So you have to write x and y in the form of u and v, and the Jacobian generally you can calculate in this form. So Jacobian, you'll be able to write this x and y in the form of uv. So you can write it like this: du by du and then dx by dv.
Yeah.
Similarly, dy by du and dy by dv. Okay, so this is the Jacobian, then that you can calculate directly. And fxy you already have. Okay, so in fxy you already have, so you'll just replace the values of xy in term of uv, because you are writing this in the form of uv, and then you need to calculate the domain of uv. Okay, so I'll just give you one example. Maybe that will help you.
So in
So
this
let
question, you can take any example in place of fxy.
Yeah, so fxy. So okay, so this is for everyone. Just try to solve this and let me know the solution. So I'm giving you one simple joint distribution of fxy, and that is 1 upon alpha square to the power x plus y upon alpha. Okay, and here x comma y, this is defined for x comma y greater than 0, and alpha is some constant that is also greater than 0, and 0 otherwise. Okay, and the transformation is been given like this: u is given as half x plus y. Okay, and v is transformed as y. Okay, now you need to calculate the joint distribution of uv. So the basic simple formula is that fxy you already have. You need to first calculate the Jacobian and then the domain of uv. So do that. I'll just wait for 2 minutes, 1 minute. So I told you the steps, right? To calculate the Jacobian, you need to see whether you are able. Okay, so this, so we make it simple: x minus y. Okay, so you are able to invert it, right? You will be able to write u and v in the term of x and y. Okay, so you need to calculate the Jacobian first. After calculating Jacobian, you just need to write, and from x and y you need to replace it with uv. Okay, that's it. And then in the end you need to see the domain of uv. Is this clear? Should I solve, or you all want to try this? Are you guys trying, or should I solve this?
So can you do it?
Yeah.
Can you solve it?
Okay. Okay. I'll solve this. See. So here, what is the Jacobian? So the first step is to write the x and y in term of uv. Okay. So I'm calculating the Jacobian. To calculate the Jacobian, I need x and y in term of u and v. So one simple thing is y is given directly as v. So I just showed y in term of uv, and then x also I can write it. How can I write? 2u, and then what?
Yes.
Plus v. So plus v, right?
Yes.
Okay. So the Jacobian would be what? So I need to differentiate it with respect to u first, so 2, right? And then I need to differentiate with respect to v, this is 1. Okay. Similarly, I need to differentiate this y with respect to u, that is 0. Okay. And then differentiate this v with respect to y with respect to v. So I got this one. So Jacobian is what? 2.
Yes.
Okay. So I can directly write now this g of uv equals to what? Fxy we already have, right? So fxy was what?
1 by alpha square
1 by alpha square.
e raised to x plus y by alpha.
Yeah, and that I need to replace with u and v. So x I
Yes.
can replace with 2u plus v and plus v, right? Upon alpha.
Yes.
Okay. And here it was given as xy greater than 0. So I need to find the domain also. And what is that? 2u plus v should be greater than 0, or v greater than 0. So from here we are getting v should be greater than -2 minus u. Minus 2u. That means v should be greater than 0. That is the one condition.
Yes.
right? So for these
So how
cases,
you
yeah,
so how you find this domain?
domain. So it's written here, right? XY should be greater than 0. So
Yeah,
in spite of x and y, we can write this, right? 2u should be greater than 2
yeah, in
plus,
terms of domain.
and then from here you need to find u and v, and that you can write it here. Okay. So for these cases, so this is the part, what you can join distribution of uv, and the condition is v should be greater than 0, and v should be greater than minus 2u, and v should be greater than 0, and u can vary from minus infinity to plus infinity, and 0 for other cases. Okay. So this is the way to transform the thing. Fine.
Yes.
Okay.
Excuse me, sir.
Yeah.
So I have a question from week 10 graded assignment.
These 10
Question number
you
4.
need to discuss with Ram.
So actually the solution we have been provided with, the question number 4 has been solved wrongly.
Okay. So let's see. Is this a problem with anyone else, or the answer is wrong, or what?
No, sir, actually there is one step. In that step, the differentiation has been done wrong.
Okay, I'll just, which week? Which week? 10th week, right?
Yes, sir.
This only, right?
Yes, so question number 4.
Question number 4th.
Yes. So the double differentiation, second derivative, the e to the power 2x we have taken out common. So there is, with sin x we will get only e to the power x.
Can you differentiate this one, right? What is this? E to the power 2x.
Minus 4 e to the power.
Okay. So this is differentiation we have to do, right?
Yes.
Okay. How then you do the differentiation of uv? You can put one as constant, and then you can differentiate the other. And the differentiation of this should be what? You can put minus 4 to the power e to x into 2. So what has been given here? So if you'll add this, you'll get some e to the power 2x, then sin x, cos x, and then minus of 8. So what has been given here?
How could you explain how you are doing the differentiation? Because what I got is e to the power x into sine
What?
sine e to the power x. This is negative, sir.
Okay,
Negative.
sorry. This will come as a negative.
Yes. And then I've got e to the power
Okay, I did the
2x.
mistake. Okay, I did the mistake. 1 second. When last time I did the differentiation. So it is about ex, and this is minus sin x, right? Sin e to the power x, and then we are differentiating ex. That is the differentiation of ex is ex, fine. And okay, and then plus you are doing, okay, and plus this you are putting it as constant, and then you are differentiating that as it is. And then it is about 2x and 2. Okay, fine. So now
Yes, sir.
I'm left with e to the power 2x and e to the power 2x, right? And this is okay. So here it will come e to the power x only. It should not be e
Yes,
to the
sir.
power 2x.
Yes, sir. That is the mistake there.
Oh, okay. Yeah, that's so, yeah, yes, okay. So the answer would be different, I guess, then.
Yes, sir.
No, the answer will be different. That I need to check. But the differentiation is wrong. Yeah, that I can issue. And then h double x, then the value will change. I don't know how much it will change, and then no.
So with the answer, I think it will be the
But
same.
the answer won't change, I guess.
No,
Yes, sir. Because
answer.
it has nothing to do with the value.
What? Can you repeat that?
Yes, sir. The answer will not change.
The answer will still remain the same.
Yeah, answer will remain the same, but the differentiation is.
Yeah.
Yeah, because you will get either after differentiation also there's not much difference in that value. Even where is that? Okay, after differentiation also you are getting such cases. Yeah, this will make this this is a bigger value, right? So this too big value, even the cos ex what will remain -1 to 1. This will also will be remaining -1 to 1. So this will make the whole equation very large negative. So the answer won't change, but yeah, I need to correct the differentiation. Okay, thank you for that. I don't know who prepared this, but okay, fine. Okay, so shall we start with the last week content?
Yes, sir.
So did anybody went through the content? 12th week? I don't think so.
Just started, sir.
Okay. So the new concept there is the EM algorithm and the basic things like okay. So the transformation that you have learned in the 11th week, that will be helpful for you in the 12th week in the first lecture. The second lecture is regarding MLE that you have already read. The third is the EM algorithm. Okay, that is new. And the last one you have already read. So if you see, only you need to go through the first and the third lecture. Second and fourth, I guess most of you already know. Okay, so I'll just go through the first week slide, first lecture slide. We'll start. This week slide. So here we are going through the standard normal vector. Okay. So what we are doing here, so I'm having some D normal standard normal distribution. Okay. And that we have written in the form of some vector, D vector, and all those V vector, D vector we have written in the form. So now we are having some sort of family, and D from that family, one family is there, that is a normal distribution, and we are taking the same sort of normal distribution, and then we are putting this in a vector that is of d dimension, and that we want to get the density equation of that z that consists of d standard normal distribution. Okay, and that can be written in this form because all the things are independent of each other, so we can directly write in the form of product. And if you are writing in the form of products, you'll get this equation. And the basic what the normal distribution we already know, 1 upon 2 root of 5 to under root 2 pi, and then sigma square, and then sigma square is 1 here, and then exponential of half of g square, and then g is simply the summation of all like z1 to zd. Okay, so this is a simple like how generally we write this d standard normal distribution, the density function of that. The main game will start from here. Like for example, I need to put it in this form. Like I have two standard normal distribution, like for example z1 and z2, and we have the transform thing also. So now I was talking about the transformation, how generally we do the transform. If we have been given the transformation of some distribution, how will we write the density equation, density function of that transformation? Like for example, z1 and z2 we already have. So z1 and z2 is the IID function, so independent function, independent normal distribution. And then x1 and x2 is written in this form. So x1 and x2 is simply the uh, transform thing of z1 and z2. So we have how generally the transformation has been done. So it's a random transformation, and the row value under root 1 minus row value, these all are taken in consideration such that the final equation or the final things that we will get in the end will be a simplified. That's why we are taking all these things from the starting, like the row y. So it's like somebody can think why we are taking x2 the transformation and row z1 only. So we can take something else also. So we just took, the professor has took this so that the simplification will become simpler, and in the end you will see a good result. Okay. So what we were doing in the starting, that I have talked earlier, in the transformation I need the Jacobian, and I need the Jacobian, and I need to see that whether I'm able to write this z1 and z2 again, or in the earlier example we saw whether I'm able to write x and y in the form of u and v or not. So here the same thing we'll do. If you'll see this, so if we'll try to write this x, so we are writing this in the form of matrix. Okay, so in the form of matrix, if you see this x1, simply you can just like simplify this also in the form of x1 and x2, and the z1 z2 also. So we'll be writing in the form of this, and here this, so he just wrote in the form of matrix and represented this as a, and the A inverse in the same thing. The A inverse, if you see, so A inverse, how did we get the A inverse? So we just tried to write the Z in the form of XY. Like we earlier we wrote X1 and Y1 in the X and Y in the form of UV. Here we are trying to write this Z in the form of X, because regarding Z we are already knowing the distribution. That's why we are trying to write this X in the form of Z. Okay. Sorry, Z in the form of X. So now we are having this A inverse. A inverse simply can work as a Jacobian for us. Okay. So here it was simple because we can get the A directly, and we can, it's 2 cross 2, we can directly get the inverse of that matrix also. And that inverse of our matrix will represent the Jacobian. We can calculate the determinant also. So in the end, whatever we were trying to get in the earlier transformation also, when we used to get the basic density function, we used to calculate the Jacobian and then the determinant of the Jacobian. Here we got the A inverse, and we can calculate the determinant to get the determinant of the Jacobian. Okay. And these are the basic things that we are doing. So expectation of x1 and x1 and x2, because the x1, you can see the transform value of z1. So z1 is a normal distribution with mean 0 and variance 1. So you can see that the expectation of x1 is 0. And similarly, you can calculate the expectation of x2 also, as it will come out to be 0. So these are some mathematical calculation, or you can say the basic properties that you need to know, like the covariance of x and y we want to calculate, and after calculating he got the value as rho. What he got? So he got, yeah, rho. Rho is the value he calculated from the covariance of x1, x1, y, x1 and x2. That's the transform thing that we need to do the transformation. So we already have the z1, z2, and x1, x2 has been transformed in the form of z1, z2. We have calculated the covariance of x1 and y1. So covariance of x1, y1 is what? Expectation of x1, y1 minus expectation of x1 into expectation of x2, right? So this can be written in this form, expectation. Okay. So x1 we already have. So x1 is what? Z1, and x2 is what? Rho into z1 plus under root 1 minus rho square to z2. That you can write it here, and you will get, after simplification, you will get the to know that the covariance of x1, y1 is also rho here. Similarly, the way he has calculated the expectation, he has calculated the variance also, and you will see why we are calculating this all. Okay. Okay. So after that, what he did, I guess he has calculated the matrix of the covariance matrix he has calculated. Okay. So the covariance matrix was that we got in the starting, we got A after the transformation, like not the transformation, the starting, that we can write this x in the form of z. So we got A and A inverse of the Jacobian. If you calculate the covariance of x, you'll get to know the covariance of x is A transpose. That A matrix we got in the starting, A transpose is the covariance of x. And the determinant that you have calculated. So you can calculate the determinant from the earlier method, like for example, A transpose, what is the determinant? So if I'm having A here, so the determinant of A was this one, so A transpose would be the square of this value. So this is what has been calculated. Okay. So here it is, the determinant is this one of the covariance matrix, and similarly the inverse of that would be 1 upon 1 minus. So that the determinant of the sigma, that sigma is being represented here, sigma inverse, the determinant will be same as whether you are calculating an A transpose of inverse and then multiply with the A inverse, you'll get 1 upon under root 1 minus sigma, 1 upon 1 minus rho square. This is the function. Okay. So now we have to calculate the final, the basic distribution, the joint distribution of x. Okay. So the basic formula was to multiply the Jacobian with the basic distribution of z. So whatever the distribution we have been given, that we need to multiply, that should be multiplied the Jacobian, and we need to replace the xy. So in the start, what we have talked in the starting, the transformation, we used to multiply the Jacobian with the distribution that was available from the starting, and in that equation we need to replace. So earlier we used to replace xy with uv. So here also we'll do the same thing. We are multiplying the Jacobian. Here the Jacobian is what? The determinant of A inverse. The A inverse we are calculating in the starting, and similarly we are replacing the values here also. Okay. So after replacing the values, what we will get to know, as this is for the two-dimensional, as we took only x1 and x2. So 1 upon, so the basic formula that we got in the starting, so this was the basic formula, right? So now 1 upon root of 2 pi d upon, like 1 upon 2 pi to the power d upon 2. So now we are having two dimensions, so 2 upon 2 becomes 1, and then we are doing like z here will get replaced with the A inverse of z, A inverse of x. Okay. So this A inverse of x, that we can write it if then earlier it was z squared, so A inverse of x can be represented. So in the, like if I'm having some A square, so that we can write in this form A transpose of x. So similarly it has been written in this form, and that is been written in this. So here minus 1 upon 2 x transpose A inverse of transpose. And so this value in between whatever, so x transpose can be written x1 x2, and similarly x can be written as x1 x2 in the column. One can be written in the column matrix, and one can be written in the form of row matrix. And this center one, A inverse of transpose and A inverse, this we already know, this is the covariance matrix that we have calculated, right? So this covariance matrix can be written in this form. Not the covariance matrix, I guess the inverse of that covariance matrix is this one. Yeah, so the inverse of covariance matrix is this one, because this is what? So it's an A inverse of transpose and then A inverse. Okay, and here the same thing was it. So here it's A into A transpose, that after inversing that we can write in this form. This is the same thing in the inverse form, right? So this can be written here directly, and the same thing. So this is the one way to expand this. The other way can be also this is the other way to expand this thing. Okay, so till now is it clear?
Yes, sir. Yes, sir.
Okay. So now, so this is the one way to expand this. The other way to expand this is this one. And after expanding this, okay, so what he did it from the starting. Okay, so now what he did is, okay, so he just kept the value of A inverse X, and he kept from where he took the values of X and Y. Okay, so he just put the value of A inverse. So A inverse we were having the starting that we have calculated after that was the Jacobian matrix. The value directly kept it here, and after putting the value so it was a squared it was in the squared form. So if you see this Jacobian matrix, so here it was what 1,0. So here you got x1 square, and for this the second column, so minus of rho upon under root 1 minus rho square. This similarly you got for x1 and x2. Like for example, minus rho of x1 upon under root 1 minus rho square and plus x2 up under root upon under root 1 minus rho square. So this we got it here, and that has been in the form. This is the mod form, so that's why it's written in the form of x1 ka whole square plus this ka whole square. Okay, and if you just replace the value, so just take the value under root 1 minus rho square and put it here. Okay, so you will see this. This is the basic. This is the this is the distribution of fx1, and this is the distribution of x2 given some values. Okay, so like for example, so here the professor told. So this we can directly say this is a distribution of this is a normal distribution with some mean 0 and variance 1, that you can directly see. Okay, so this is the distribution of this is the normal distribution with normal distribution of x2. Here the mean is rho x1 and the variance is 1 minus rho square. Okay, that you can see it from the equation that we have got. So this can be written in this form. So this has been written. So, and we already read about the stats too also. Like if you have been asked to write the joint distribution of fx here, so you can write it in this form: fx1, the density function of fx1 multiplied with f. So simply the marginal into conditional form. The like you have read the joint density distribution can be written in the form of conditional multiplied with the marginal distribution. Okay, that you read in the stats also. So this is the same thing we are doing. Like after doing some mathematical calculation or the calculation, we are just writing some changing or interchanging the values here and there. In the end, we got in this form. So this joint distribution can be written. So from the starting, we were taking x1, x2 only, and this can be written in the form of distribution of fx1 multiplied with the conditional of x2 given the mean and the variance has been given. Okay, so this is the same. So now we are having this is simply the multiplication of two distribution. One is the x1 where that belongs to the normal distribution with mean 0 and 1, variance 1, and the second distribution is x2 given x1 where the mean value is rho x1 and the variance is 1 minus rho x1. The same thing has been shown in the picture, like this in the scattered plot. He wants to show the same thing. So what you can see is in the second equation, x2 given x1 equals to, so if I'm having the scatter plot, or we can say if from this family, if I want to take some data set, if I'll take some sort of data set from this family and fixing the value of x1, if after fixing the value of x1, you will see that whenever we will take the data set, the bunch of data sets, so in the middle where the x2, where the mean will be rho x1, okay, at that point there will be a chunk of data set. So this is what we can prefer, or we can refer from this equation. Okay, so x2 given x1 is a normal distribution where mean is what? Mean is row x1 and the variance is 1 minus rho square. So, so this was the scatter plot I was having. So what he did, he just took some chunk of data set from there, and after fixing the value, so here this was a continuous, so we can't take the exact value. So we'll just take a boundary. Like for example, if I'm putting x1 equals to 2.5, that means we are taking the value from 2.45 to 2.52. Okay. So this is the chunk of data set we are taking. And after fixing, so here the x1 has been fixed. And if you see this, so this is what? This is normal distribution only, because the x2 given x1 was a normal distribution where the mean was what? Row x1. So you can see this where the x2 equals to row x1 line. You can see this here, the chunk, most of the data set is here at the where the line is crossing the data set. Why? Because here it is, the mean is here. That's why most of the values or most of the chunk of the data set are available here. So this can be seen from the pictures also. Okay. Is this fine?
Yes, sir. Yes.
Okay. So this was the main thing, I guess, in the first, and then by some basic properties he wrote in the form of the same thing, and this thing will use in the EM. So EM equation algorithm when will be EM algorithm is simply the chicken egg problem. So which came first? So this type problem, like for example, if I'm having distribution like for the Gaussian distribution, and I don't know about the parameter also, and I know like for example in the clustering generally we use. Like for example, I'm having three fruits like pomegranate. I'm having some fruits like apple. I'm having or some third fruit like for example banana. I'm having. So out of these three, so like how does it work in clustering? How does it work? So how like for example in the starting I'm having only the data set. Okay, so how does that algorithm will work to know? Okay, how does it work? Like we are not doing anything in that. We are just trying to applying some basic algorithm. Like for example, the K-mean algorithm I want to apply, and then with that with some basic clustering algorithm I want to know how many type of things are there. So how many clusters are there? Like for example, I took three clusters. One is banana, one is pomegranate, and one is apple. Okay, so three clusters are there. But from the starting, we are not knowing this three clusters. Okay, so with some clustering method, we need to classify that. Okay, the k is equals to 3, and then we need to, so that whenever the new things will come, that will get clustered in the, like for example, I'm taking the new like new apple and thing. So on the basis of some clustering method, it will just classify on that. So that okay, this belongs to the third category of the fruits, right? So this will see in the EM algorithm how does that work. Okay, this is one of the basic algorithms. All the other algorithms will be reading in the MLT and all. So this is just a basic starting point of that. Okay, so this is what has been discussed in the first lecture. I think so. After going through the lecture, you won't face much issue in this first what do you say lecture. And activity question is also not that difficult. So these are all pretty simple. This only is the only question that you need to solve. Other than that, all the questions are theoretical based. So this also can be solved pretty simply. Like for example, you have been given the y mu also been given. So y1 is having the mu value as 3, y2 is having the mu value as 1, y3 is having the mu value as 4, and the sigma matrix is also been given. So what does that 6 represent here? Can somebody tell me that 6, or what does that 13 represent here?
Variance.
What? Yeah, variance with what? Like 6 is what? Which variance? Like variance of what? Y1 and Y2, Y1, Y1. What is that?
Y1.
So this is simply a covariance of Y1. So if you have to calculate the covariance of X, Y1, Y1, that means the covariance. Okay. So then in the diagonal of this matrix will represent the covariance of Y1 and Y2 and Y3. Okay. So if you need to calculate the expectation of Z, how will you calculate the expectation of Z? Can somebody tell me? Okay. Okay. So fine. If you so this can be solved like for example you have to calculate the expectation of Z. So you have been given the C already. So C is the matrix and then you have the U matrix. Okay. So CY. So see the mean matrix of Y is what? This one. So you just have to do the product multiplication, the matrix product multiplication of that matrix. Okay. So you get the expectation. Similarly, you can get the variance and then you can calculate the other things. That this type of problem is there in the graded also. So okay, fine. So the first lecture is clear, right? So is there any issue in that? Is there any problem in that? Or should I go through the second one? Is there anyone or what? Am I audible or not?
Yeah, you're audible, sir. You can go ahead.
Okay. Okay. So the next part is what? The next part that we already have read in the stats 2 regarding the estimation of the parameter using the maximum likelihood function. Okay. So maximum likelihood, I'll just go to the brief of that maximum likelihood because most of you are aware of this method, how to estimate the parameter. Like for example, you already got some family, like for the family of the distribution. And the some, like for example, you already know that whatever the data set I'm taking out, this coming from some family and that family belongs to normal distribution. Okay. It can be normal, exponential, whatever you want to know. Like all should be independent of each other. And so that distribution that I'm taking out the data set is a the normal distribution, like for example. Okay. So the normal distribution generally has some parameter. Like for example, the normal distribution has the parameter mu and variance. So if I'm taking out some data set, so I should know like so from where I'm getting the data set. Okay, I'm knowing the normal this is coming from a normal distribution, but I'm not knowing about the parameter from the if I'm not knowing about the parameter, I can't say anything about that, right? So if I'm taking out some data set from some normal distribution of the family, so I should know about the parameters. So like for example, if I'm having the chunk of sample data set, from the sample data set only if I'm to predict the value of the if I want to predict the parameter, I want to estimate the value of the parameter. So there are many methods like the Bayesian estimation you would have done, or the moment method, or the one method is simply the maximum likelihood method. So here, simply we'll go to the maximum likelihood method, not the other Bayesian or other moments method. So in that maximum likelihood method, we just write the likelihood function, and likelihood function can be written like, for example, the probability of x1 equals to, so like for example, I took some data set, like for example, I took data set 10 data sets, and 10 data sets I'm having. So we can write if I'm having the, because I know the normal, the function or the normal, the function of the normal distribution. We are not aware of the parameter of the normal distribution, but we know how to write the basic density function of the normal distribution. So from the basic density function, if I'm having 5 data set or 10 data sets, so for all those 5 or 10 data sets can be written in the form of product of, like for example, if I'm having the x1 equals to 5 and x2 equals to 10. So for x1 equals to 5, I'll just put the value x in the density function, and then we'll do the product with the other data sets also. So this is simply a likelihood function, how likely that is going to happen. Okay. So that you can write in the form of probability only with the parameter value. Like for example, I took the parameter as mean as some mu, and then variance as some random stuffs I took. And then I wrote the likelihood function, and likelihood function, you can take the log and differentiate it, equate it to 0 to get the estimated value. There can be some other methods also, like you read about the gradient descent, and also those methods also can work here to know the estimated value, right? We have the objective function now. So this is the objective function that we need to reduce, or you can say from here, like here is r theta is the objective function, and you need to estimate the value of parameter, and you need to minimize this function and get the estimated value. Okay, so this is the one method. If your family is a normal distribution. Similarly, if you have family of Bernoulli distribution, you are getting all the data sets from some Bernoulli equation. So Bernoulli is quite simple compared to the normal distribution, because normal distribution generally have the two parameters. Bernoulli generally have the one parameter, only the theta or the p value. Okay, so this can be the likelihood function, and then you can take the log function, and then this needs to whether you are maximizing those function or after taking the log. So if you are having minus at the starting, then you can minimize the function, okay, to get the parameter estimation. So this is the other, if you are having the Bernoulli distribution, you can do it like this. Similarly, you can do it for, like, for example, in the end, theta MLE was this one. And that you all know that this is the best method to estimate the value of the value of parameter in the Bernoulli equation. Similarly, for the uniform distribution also you can do, and in the end you got some random stuff. Similarly for the normal distribution, because for the normal distribution you are having the two parameters. So if you have been given one parameter, you can estimate the other parameter with the help of MLE. Or if you need to estimate both the parameters, you need to go through some, because it's a hard problem. That's why you need to solve using some not the hard problem, but you need to go, if you have to calculate both the parameter and you have not been given anything else other than that sample data set, you can solve those problems with some gradient descent methods also. Okay. So this is what has been discussed in the second lecture. Nothing else is there in the second lecture. Most of the concepts you already know, and the problems also in the second lecture is not that difficult. All the questions are related to MLE. You just have to like the likelihood function, differentiate it, and equate it to 0, minimize that or maximize, whether, like, depends on you. If you are taking the minus of log or what you are taking, so you need to maximize and minimize to get the value of parameter. The third lecture, you'll be going through the Gaussian mixed-energy GMM model or the expectation maximization. Okay. So second lecture, does anybody has any issue? Is there any issue till now? Okay, so how will I know whether you are listening or not? I don't know.
You are listening.
Okay, so I'll just go through the third lecture, that is related to the GMM model, Gaussian mixture model. So, like, for example, I'm just taking, so there can be some data set, like, for example, I'm taking the data set of a student, of some students. So, like, for example, this is a, and having the three pick. Three pick means I'm having the data set. For example, in a classroom, like, there are 4 types of people or 3 types of people. So I'm having some multiple choice question, and within that multiple choice question, we just marked AA for all the questions, and he got the marks. And all those chunks of people are here in the pi 1. And the chunk of people who just marked B as an answer in all the cases, all the questions. So this is the chunk of people that represents pi 2. And the chunk of people who just marked 3 options. So this is a so this is the chunk of people pi 3 that marked 3 as an answer, and this is the chunk of people there. So now we are having the 3 peak value. So one peak is at, and the people who marked A as an answer has got the mean value of the marks is -4. Similarly, for the chunk of people who marked the B as an answer has a mean value at 0, and similarly for the chunk of people who marked 3 or the C as an answer for the question has got 5 as a final marks. Okay, so now we are having 3 peaks. Okay, and the 40%, like for example, here from the data source, from the plot, we can see this 40% of the people has marked A as answer, 30% of the people has marked B as answer, and 30% of the people, 30% of the remaining classes has marked C as answer. This is the plot that we got from the data set from the after doing some analysis. Okay, so this can be plotted in a single plot. Like for example, in the second graph, you can see this. This has been plotted in a single graph. This is a simple GMM model where we are having 3 picks. Okay, 3 peaks, or you can say this is a type of 3 having a data set with the 3 clustering. Okay, so now if I've chosen some student and I want to know from which section or from which chunk he came from, we need to do some analysis, right? So for example, the person who has got 0 as a mark, 0 as a final mark, then we can see that this student has come from the second chunk of P, right? So if I'm having the data, if I'm having this plot and the data set, we can directly say that from where this chunk has came. Okay, like, so for all these 3 peaks, like for example, I was giving you some clustering example. So if this is in the form of normal distribution, and I'm having the parameter, if I'm having the parameter and then I've been given the data set, then I can say that this data set has come from this cluster. But if I don't have the parameter of the cluster, then we can't say from which plot or from which chunk distribution this is coming. Like for example, 3 peaks I'm having, 3 clusters I'm having, and I've been given the data set. I can't say if I don't know the parameter of those 3. Yes, even if you've been given the data set in the ML data science, you will not be knowing about how many clusters are there. So even you are not knowing about how many clusters are there. So how can somebody tell you about the parameter of those clusters? So if you don't know about how many clusters are there of the data set, you can't predict or you can't even know about the parameter of those cases also. Okay, so there are some methods that can help you in solving those processes. Okay, so this is the basic density function. That how will you write this GMM model? So you are having the 3 peaks. You can write this in the form of weighted mean weighted what you can say, the weighted distribution. So you just have to write the how many percentage of that how much percentage of that, like for example there the pi1 was 40%, so you need to multiply that distribution is 0.4 and do the summation with all the remaining distribution. Like for example the pi2 was 30%, so you need to multiply 0.3 with that density function, and then for the third cases also you need to multiply that whatever the chunk is there. So this is a basic what you can say, the basic density function, how you need to write. Okay, so here for example I was having this cluster. So if you have just plotted this data set, you can directly say this. But if you have been given with the color coding also, like for example this one cluster is red and one cluster is blue, so if you have been given the data set, you can directly say, okay, this is coming from red cluster and this is coming from the blue cluster. Or if you know about the cluster, if you know the parameter of the cluster, you can directly say. But if you, like for example, this both the cluster was red or both the cluster was blue, and then you have been given the data set, so how can you then you will not be able to say from which cluster is coming, because earlier you were knowing about the color code or the you were earlier knowing about the parameter, so you directly told, yeah, okay, this data set is coming from this parameter, this chunk or this cluster. But if you have not been given, you can't say about that. Okay. So there is a method. One method is there. Okay. So like for example, okay. So there's a method that we'll discuss later. First, we'll go through this data set. So in the first plot, you can see this. In the first plot, the color coding, or you can say the parameter has been given. So if you have been given the data set, you can directly say, okay, this is coming from the red cluster, or this is coming from the blue cluster or the green cluster. But in the second plot, if you are given the data set, you can't say anything about that because all the color code or the parameter has not been given, so you can't say anything about the second diagram. Okay, so there is a method for that. That method generally we call that as a expectation maximization method or the EM method, EM algorithm. So in EM algorithm generally starts with, so which come first, whether the chicken or the egg. So that means we are like, for example, I'm giving you some three data sets. Like for example, I gave you three data points, and in that three data point, I am not telling you the third data point. And if so, like for example, I'm giving you some example here. So in the first case, that if I'm giving you 1, 2, and some what, and then I'm telling you this is coming from some normal distribution 0, 1, and then you need to predict the value of this value, and then you need to predict the value of that data point. You can directly say if this is coming from. If you have to calculate, like for example, this data point is not been given, and you were having only three data set x1, x2, x3, and you need to ask what is the mean of these three data sets. If you have been given this parameter, you can say, okay, 0 is the like the expected value that should come as a mean value, right? So you can say that the mean value can be 0. If you have been asked to, if you have not been given the third data set, and you have been given regarding the from where the data set is coming, and you have been asked to calculate the mean value, you can say that the okay, expected value of this data set can be 0, because the from the data set from where this distribution is coming having the expected value as 0 and the variance as 1. So you can say directly this is coming from 0, right? Are you there?
Yeah.
Yes.
And the second, if you have been given all the data sets and then you have been asked to calculate the mean, you can calculate that, right? So whether one thing should be given, whether you are available with the parameter or the data set. If you have not been given the both the things, then it's pretty difficult to calculate, right? So what we are doing it here in this here, what we are trying to do. So we are going with some method, like here we are dealing with the expectation maximization method. So generally have two steps, that the one is E and the second is the M step, the expectation step or the E step generally we call this. So what we are doing it here. So I'm having some clustering. The cluster we already have, but the number of clusters we don't have, and we don't have the parameter also. Like for example, if somebody has told me regarding the color coding or the parameter, then we can directly say for the new data set, we can directly say this is coming from this data set. But if we don't know about the parameter values or the parameter values, so it's pretty difficult to say that. So what we'll try to do, we can in the starting we'll just take, like for example, I'm having some data set. So from the starting itself, we'll just we'll just start taking some random values. Okay, so like for example, I'm having data set. I just I just not predicted, I just thought that okay, the k value belongs to the k value. I know, like for example, I have the k value as 2 or 3. So what I'll do, I'll just for two clusters, as I'm fixing the k value as 2 or 3, so I'm like, for example, I'm fixing the value k as 2. So if I'm fixing the value k equals to 2, so what I will do for those two fixing value, I'll just give some parameter to both the cluster. Okay, so I'll just give two parameters. I'll give the parameter mu and variance for both the cases. Okay, and then if I'm having the data set, and for those data set, I just thought, okay, this data set is having two cluster, and for those two cluster, I just gave some random parameter value. And now if I'm giving the first step, I'm just giving the random parameter values, and after giving the parameter values, I need to start updating that. Updating that means, like for example, I just took one data set and then calculated the cluster responsibility for that. And I calculated the cluster responsibility for that, and then I saw that in which case it is going. So for both the cluster, so there is a fixed formula for that. That is not fixed formula. This is a cluster. So I'll tell you the cluster. This is the response. Yeah. So this is the method to calculate the cluster responsibility. Like for example, I'm plotting a graph. If I'm having this plot, I just from the random I'm having some data set. This is a data set I'm having in the starting. Okay, and this is the plot I'm having. Okay, so I'll calculate the cluster responsibility. So this the parameter for this and the parameter for this I just took randomly in the starting, because I don't know about anything about the parameters. Okay, so just I took some new a variance sigma a square I took for this one, and mu b sigma b square I just took for the second cluster. Okay, so in the starting I'm not knowing about anything. I just only have the data set. I need to find a way to make I need to find a way such that this can be classified into clusters. Okay, so I just fixed the value of k as 2, and then I took some random parameters for these two cases. Okay, I just took the value mu a and sigma a square for this plot, and for sigma b mu b square for this plot. This I'm taking just randomly. I don't know about the anything. I just know, okay, k equals to 2. So I just took some two parameters, and what I did is I just calculated the cluster responsibility. Like for example, this data set I'm having. So I just took the one data set and then calculated the cluster responsibility. Like for example, in the form of probability. So the probability of going this data set in this cluster, the A cluster is this much, and the probability that this data set can go into this cluster is this much. So you can see that the second part, the probability value for the second, the probability for the this data point to go in the second case is much higher than that of the earlier one. Okay, so after updating the second case, what I'll do is I'll update that. Means what? This data set will go in this data set as the cluster responsibility or the probability value is much larger for this B as compared to A. So this data point will move to this cluster. Okay, and what? So now I'm having some data point in this, and after having this data, after having the data set in this second cluster, so I'll update the value of nu A, nu B, and sigma B. As the value will start changing. Are you able to hear me?
Yeah.
Yeah. So what I'll do is now I'm having this data set, and after getting the data set, now calculating the cluster responsibility. After calculating the cluster responsibility, I came to know that this data set belongs to the dummy parameter that we have created in the starting. Two dummy parameter we have created, and this data set is belonging to the second dummy parameter. So I'll just put this data set in this, and now I'll update the value of nu b and sigma b again, because and now I'm having some data set, so I can update the value of mu b. Okay, so this will start converging to the exact mu b and mu b square. So for all the data sets, I'll start doing the same thing. We'll calculate I'll do the E step, I'll do the M step, I'll do the E step, I'll do the M step. So I'll just calculate the cluster responsibility. I'll put this in the whichever the cluster responsibility for whichever the probability is higher. I'll just put that data set in that the desired cluster, and then calculate. Then I'll update the parameters. And after doing this n number of times, if I'm having the n data set, so this will start converging. So the parameter will start converging to the exact cluster, the exact value. Okay, and in the end, we'll see that this will start getting converged to the original value, and then the data set will get will in the end we'll be able to find the clusters also. This data set is belonging to this cluster. Okay, so this is what has been done in this. Like for example, this was the plot. So the two dummy cluster has been taken, and then from the starting we started doing the E method, EM we started doing, in the end after doing this we came to know that this is the one cluster and this is the other cluster. So we can see that the basic step we are able to find the two clusters, and we are able to differentiate between the data points also, which data point is coming from which cluster. Okay, I think so this is clear. So if you're having any doubt, you can ask regarding the EM algorithm. So then I'll move to the last lecture, and the last lecture is generally that you already have studied in the stats 2, stats 1 also, the Markov and the Chebyshev inequality. And I don't think so this needs to be discussed because you already have read 2-3 times. So I'm not going to discuss this Markov's and Chebyshev inequality again and again. So you can just go through the slides or the lectures itself, and you'll be able to understand it. So only the one thing that was required to be taught was the EM model, EM algorithm, and the first part was the how to write the density function in the form of transform things. And now we have discussed about the SAM having D normal, standard normal distribution. How will you write the density functions, and how will you will be able to find the density function and all. So we discussed those things. So this was the only two things that needs to be discussed in the 12th week. I think like everything else has already you read about the Markov, Chebyshev, and MLE models and all earlier. So I don't think so. If you are having issues, you can ask. Otherwise, it's fine. You can just go through the slides and you can solve the problem. Is this clear to everyone? So, if anything needs to be discussed regarding this week, any doubt in the problem and all, if anybody has solved.
This before end term, how many revision sessions we'll be having?
We will have 3 revision sessions.
All those will be kind of problem solving sessions, right? With respect to end term.
Yeah. So we'll discuss the concepts, and if you find any issues in any of the problem, you can just discuss it there. And what in the end, I will take one session, like in the included one, I'll take the one session where I'll discuss the important concepts or important problem I can discuss in the end.
We would need basically 1 or 2 sessions wherein the problems which are important, the type of problems which are important for the end term examinations, and samples just online let us solve it. So that will make a lot of comfort feeling.
Okay, so one session I'll take in the end for those last 3-4 weeks, because those 3-4 weeks are the most important one. So I'll just discuss the some problems from this 3-4 weeks, from the 10th, 11th, 12th, or 9th, 10th, 11th.
9, 10, 11, 12, right?
Yeah.
So what would be the kind of combination? Like it will be 60% from these 4 weeks, or how?
Usually from like you'll get a 40 to 50% from this 4 week only, and then the rest will be from 1 to 8 weeks. So any other doubts if you're having, you can ask. So the unit exam is on 7th August, I guess.
Yeah, it is 7th August.
So we'll take the session, the revision session starts from next week, I guess. One more session is there on the Saturday. We'll just discuss some problems from 12th week. Yeah,
And
and next,
Saturday it has to be 11th week, not 12th week. I think the graded assignment deadline is 27th. So, and 24th is for 11th week.
no, the 11th week we have already discussed. Yesterday we have discussed some problems.
Okay.
So 12th week, so on the Saturday we have for the 12th week only. And then from the next week we'll start the revision session. Because the next week only, next I will be having next week 2 weeks. We'll have to maybe 3 or 4 sessions regarding revision.
Yeah, for that, what I feel is that let us pick problem, then discuss the concept in that problem and solve it. And then like that, if we can move, that would be better rather than concept
Okay.
first, then problem. That makes it difficult. Actually. You can pick problems, then the concept in that problem, then how to solve it.
Okay. So I'll just tell them to take the sessions, like to solve some problems in the session also. I'll ask Ram to do that. And I'll also do the same thing for the last 4 weeks. That I'll take the session.
The whole thing towards the end term exam only, we should focus toward the last 4 revision session, because clearing that exam will be the focus there.
Yeah, and the exam, the problems will be also a bit difficult than the quiz.
Yeah.
Okay, so I'll just
What is the difficulty level of the exam? There, I think it is 1.5 hours long, but how many questions and what?
So there was number of questions only much, like 16 to 17 will be there. So earlier in the questions, like in the quiz 1 and 2, there were like 13 to 12 to 13 questions for 1 hour. So the number of questions, 3-4 questions will get increased, and the difficulty will be almost similar and a bit, like you can say, a bit more than the quiz second.
We would need sample problems actually.
Yeah, mock will provide you. Mock will provide you by Friday this week. And then in the revision session, we'll discuss some problems on the same pace of the final quiz exam. Last time also, in the quiz, for the quiz 2 also, we take the session, we discussed it. Like I personally discussed some problems that was on the same pace of the quiz 2.
Yeah.
Yeah, so we'll try to do that for the final quiz also. And there won't be any, so in the quiz 2, there was some errors, like 3 errors was there. We'll try to minimize that. So, yeah.
And it will be helpful if you can share some tips on how to solve the problems faster. Like last time you had told us about that getting that eigenvalue quickly.
Yeah, so we'll try to do that. I'll just see the which sort of problems are there, and then we'll discuss in the final revision session. Some problem we'll discuss on the same page, on the same level of the questions that I see in the final quiz. So maybe that will help you. So do attend the revision session. That will happen next week. I need to fix it when we have to organize that. I'll just have to first finalize the final quiz. So we are finalizing that only, and then next week we'll have that session.
And then time also, if it is like 6 to 8 or something, that would be better.
Okay, so I'll try to make it 6 to 8 or 8 to 10. Okay, so
Yeah.
okay, revision session I'll take it in the evening itself. I'll not take it from 2 to 4. Okay.
Yeah.
Because this was the only the slot I was getting free. That's why I was putting the that's why I was putting from 2 to 4. There are so many like courses going on, so I was not getting the slot. I'll try to get the slot for that revision session at least. Okay, so one guy, Venkatesh, is asking to increase the number of questions so that the marks per question will be distributed equally. Okay, I'll try to do so. If we'll increase the number of questions, it will become difficult for you also to solve that, right?
I think what he meant is that if you take one question and divide it into sub questions, then
Okay.
time will be the same, but marks will be distributed. So
Okay.
if you make a mistake in one of the steps, you will not lose the entire marks.
Okay. 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 So I'll try to do that. The sub part, I'll try to make some sub part of some questions. Not for all, but at least for 3-4 questions so that you help you. So it's like, for example, if I need to prepare some question on SBD or something, so how will I prepare that? Like the subparts should become, okay, yeah, we'll try. Okay, we can do that for some eigenvalues and eigenvectors. Okay, I'll try to do that for some questions. Okay, anything else, guys? Okay, then I'll try to, I'll close this session. Is this fine? Anybody is having an issue, you can ask, otherwise we'll close this. Should I close this?
Yes, sir. So,
Yes.
Okay, thanks everyone for joining the session. Thank you, Venkatesh. Thanks.
Thank you.
Yeah, thanks.